Okay, everybody, as I promised, I'm doing a supplemental broadcast this week because I want a screencast because I want to spend our time Wednesday on the outliers case. So we're going to look at the Burger Dome case, and I'll go back over here to the modules for a moment just to remind us what we've got going on. And here in Module 10, the quiz over Anderson, Chapter 11, is due on the 12th, as is the outliers, that file. And we're just going through the file, and so all you need to do is just upload it. The single Burger Dome, it does have a problem attached to it, and we'll look at it. And then I have some more resources here for us to work with when we work on the outliers case, as well as resources on z-score calculations. And in the outliers case, we're going to create z-scores, and this calculator will give us the probability that we would get that z-score. Then I've got some more resources about our return on investment analytics, and this are a couple of things that deal with queuing theory, customer satisfaction, and wait time, and then how long will customers wait for service, because we're covering cases that deal with queuing theory. And the Burger Dome case, also known as single, is over here in Chapter 11 in the Anderson text. And you'll see I've done a search on it. That's the nice part about this digital text, is I can just do a search. And here we've looked at the structure of a waiting line system. We've covered some of that. And this is a single server waiting line with Poisson arrivals and exponential service times. And Burger Dome, the case is called single. It's there in the Chapter 11 file. So we'll go. If you go back into the files in Canvas, and you'll find if you look in Canvas in the files section, and you look for the Anderson files, okay, the student Excel files, and then go to Chapter 11, and you'll find the single. I'm going to grab it here, and here they are. And we'll just look at it. And this is the single. We looked at the single arbitrary last week, and this time look at the one called single. So I'm going to copy it and then paste it over here on the well, I thought I was pasting it over here on the board. This is just, the interaction of these things are just so strange. Let me try this again. Weird. I'm going to go ahead and open it up. And I'm having some issues with dragging and dropping these. I don't know why. And I'm going to enable the editing. Okay. And then I'm going to go ahead and save this file. And I'm going to put it on my PC. And I'm going to put it on my desktop. And it's called copy of single, I'm going to put Harmon so I can save it on a desktop and have a copy I can edit. Okay. All right, now this is the single server waiting model. This is for Burger Dome. And I'm going to go back over here for a moment. And we'll go back to the modules. And here we're asked to, we're given the instructions. As I mentioned, you'll want to review pages 511 through 516. Let's see if we have anything else. We've got everybody there. Copy that. And then I'm going to go back here to my file. And I'm going to insert a text file. Find a place to insert that. I'm going to insert a little text file. I find my icon to do that. And somewhere in here it's lurking. It's just strange. Insert a text file. And I want to find this icon so I can insert it. Yes, I have to click. And I'm going to insert a text box. Sorry about that, folks. It's late and I'm tired. All right. Now I have a key for this over in the next module, so if you'll want to upload it or follow my steps along here. Let's look at the case for a moment before we start manipulating any data. And it's going to start over there on page 511. Okay. And here we're looking at what we call the Poisson probabilities for the number of customer arrivals. And this is at Burger Dome. This is the case we're working with during a 1 minute period. Okay. And they tell us that the population mean is 0.75. So here are the number of arrivals. Now remember, Poisson is based on kind of a stair-step approach, which says we kind of have a steady state, and then a bunch of people come in to be served, and then we kind of go back to steady state, and then we go up again. And that's customary of any place where there are going to be some arrival times that are random, but there will also be some arrival times where the bulk of the distribution of those is going to come at a particular time, like the dinner hour, lunch hour, breakfast, okay? And so we have the probability that we'll have a certain number of arrivals, and that's our distribution of service times, and the authors talk about this, and they give us the probability of the service time, and that's the mean number of units that can be served per period. And there's the eigenvalue, and that's the formula for the exponential probability distribution. Okay. And so as they discuss server times, the server times are rarely constant, service times are rarely constant, and they walk through the process of the distribution of the service times, and they walk us through the math of how they got those probabilities for a service time being less than half a minute, equal to or less than a minute, equal to or less than 2 minutes. And so we can see the and the authors give us some, over here in the note, the property of exponential probability distribution There's a 0.6321 probability that the random variable takes on a value less than its mean. Okay. And so when we talk about half a minute or less, we're just basically saying this is the mean and the eigenvalue applied to it. And that's how we get those probabilities for service time. They talk about Q discipline here, okay? And they talk about an FCFS Q discipline, that is first come, first served. And they walk us through some of the different scenarios. They're a little bit different. For example, airplanes, have the passengers' seat assignments in the back of the plane board first. It makes only sense. And they talk about hospitals, emergency rooms having to create their own Q discipline. Steady state is when we're in a transit period where we're between a lot of service, and they begin to give us the model here. And as I mentioned before, queuing theory, we could have a whole course on it, so we just barely brush the top of this. So if you go, boy, we blew through that fast. Yes, we are. It's an introduction to management science. Queuing theory is, again, waiting line theory would be its own particular course. So we're just getting the highlights. And then we start to look at the operating characteristics, and they refer us over to Appendix D. Okay, if you want you really want to know about the mathematical development of the formulas. And here we have the characteristics. The mean number of arrivals per period, that's the arrival rate. And then we have the mean number of services per time period, the service rate. Okay. And so we're getting those, and then we'll go on through the operating characteristics. And here are the probabilities. No units, probability that we have. And here's the average number of units in the waiting line, the average number of units in the system, the average time a unit spends in the waiting line, the average time a unit spends in the system, the probability that somebody's got to wait for service, and the probability of a certain set of units in the system at any given time. They give us the formulas for that. Right. And they note something up here at the top. These don't provide formulas for optimal conditions. These talk about the steady state operating characteristics of a waiting line. And they then walk us through the operating characteristics for a burger dome. And you remember, we have a single server waiting line. So we have people who arrive and they're waiting. We have people who are being served. And the people waiting and the people being served are the number of people in the system. Okay? And because we do first come, first serve, the next person in line is taken care of. And they work this all out for us in terms of customers and in terms of minutes. And here's the probability of the customers, the number in customers in the system for the Burger Dome waiting program. In other words, here are the probabilities that we'll have 0 customers all the way up to 6 and then 7 or more. Okay. This is the number of customers in the system, period, total. Remember, we started back looking over here, and we looked at the customer arrivals, okay? So we're, again, using management science. We're using the Poisson distribution. And we're assuming that in this type of operation that that's going to be applicable. And then we use probability theory to calculate the number of arrivals. And then the probability that people will be waiting. Then we come to the number of customers. So the number of customers are going to be those who are waiting and those who are being served. That's the total number. We're concerned about the arrival time because that's going to lead, of course, that's going to augur for us the number of people who will be waiting. And service times, we've talked about those as well. They give us some ideas here about how managers try to work with waiting lines and to use them. And again, the value of the model is only as good as the numbers you put into it. So this is, you know, these probabilities and the numbers that we put into them really do have to be based on some solid math, but also some good numbers from the real world. And you could build some operating characteristics from past experience, okay? In fact, most service establishments, if you have a single server or multiple servers, you're going to have different kinds of operating characteristics based on the day of the week, the hour of the day, or even the season of the year. So it's not as simple as I find a model and I apply it every day. It just won't happen like that at all. And they talk about improving waiting line operation. And here's this trade-off between waiting line, people waiting in line, versus the additional value, the additional cost of adding another server. And so it becomes a trade-off between how long we let people wait versus, well, we open up another serving line and we're going to reduce waiting time, which might keep some customers, but by the same token, we're going to increase our costs. This is very much like that total cost analysis that we've done before. And they give us operating characteristics. If the service rate is increased to 1.25 customers per minute. And you can see here in table 11.3 what we end up with. Then they start to give us the Excel solution in the model, and we're going to take a look at that here in a moment. And they give us some notes and comments in terms of some of our assumptions. For example, if we assume a Poisson probability distribution, then we assume that the time between arrivals has an exponential probability. And notice what they tell you. For example, they say, for example, this is in the notes and comments, if the arrivals for a waiting line follow a Poisson probability distribution with a mean of 20 arrivals per hour, the time between arrivals will follow an exponential probability of 1 over 20, or 0.05 per hour. And they give some discussions about service rate versus arrival rate. And the caveat, even though we have variability of arrival time and service time, we can keep and still get long waits when service rate exceeds the arrival rate. Okay. Again, as I said, this starts to get complex pretty fast, especially with the probability theorems that are used. Appendix D has those. You can go over and study Appendix D to look at the dynamics of a situation. Again, it's going to be you really are balancing off an uncontrollable versus a controllable factor. The uncontrollable factor is as you would guess, the arrival time. Okay, really two uncontrollable. I'm going to say an uncontrollable factor, a semi-controllable factor, and what should be a very controllable factor. The very controllable factor is service time. You should, through training, etc., be able to have that within reasonable bounds. Waiting time is, I would say, semi-controllable because you can do some things to conduce people to stay and to not simply leave, but there is a threshold where they'll go. And to accommodate them, there's going to have to be something there to keep them. Then finally, the arrival times are completely beyond your control. Restaurants will try to do this. For example, they'll say our happy hour is from 5 till 9. Why? So they can lure a bunch of people in, or all a cluster during dinner hour, and maybe people will do the happy hour, and so you're going to get crunched at that time. Okay. Some will try to take slack times, and if you're not doing, or maybe use lunch times and offer specials for lunch, that type of thing, or certain days of the week they'll offer some kind of a deal. This is a way to increase the arrival rates, period. Okay, so if the arrival rates go up, then the arrival time itself will go up. Well, let's look at this and see and see what we get. So I'm going to go back to our Excel file that we had, and here's the single server waiting line. This is Burger Dome. And they give us some instructions. We're going to use goal seek to obtain a probability that an arriving customer has to wait 0.55. Okay, so we're going to use goal seek. So we're going to click data. And that's going to be under the what if analysis. And the arriving customer has to wait 0.55. So we have the probability that they have to wait. Okay, so we're looking at, and we'll just do the goal seek now. The probability that an arriving customer has to wait 0.55. So, and we want to change that to 0.55. Okay, and by changing the service rate, the wait time scenario. Okay, scenario 1, by changing the service rate this is our first scenario, and then use the goal seek. We have two scenarios here. We're going to use the goal seek, okay, to obtain a probability an arriving customer has to wait 0.55 by changing the service rate, wait time scenario, okay, and the changing cell will be the service rate. Okay. And let's see what we get. And here we are. Now, this is our first scenario, okay? And let's take a look at what's happened here. Now, we changed cell C18, and we found a solution. The target value was 0.55, and we've hit that. You can see that. We changed the service rate, and that's wait time scenario 1. And we found that we changed the service rate to 1.36. So we're serving more customers. The service rate tells us that we're serving the customers. We were at 1 and now we're 1.36. So we've made a roughly 36% improvement in service time. Okay. And because we've improved service rate, we have improved the amount of time we have lowered the probability that somebody's got to wait. Okay. Now let's just go over here for a moment and we'll cancel that. That's all we have to do. And then what we could do is we could click, just go ahead and we could add another tab and we'll say okay. So we've got our scenario number 1. Okay. And scenario number 2 is we want to obtain the probability that the customer has to wait 0.35 by changing the service rate. Again, it makes sense. We're going to do the goal seek. And we're going to set the cell to 0.35. Okay. And we're going to change the cell. We're going to change the service rate time. Now let's see what we get. And we should see that service rate goes up as the probability of waiting goes down. And for sure, there's a solution. And we have to double our service rate to lower that probability. Okay. Now, this is a common sense. This is very intuitive. You say, okay, the faster I serve people, the lower the probability that they'll have to wait. Makes sense to me. And again, we've used management science to look at probability theory, use a Poisson to set up all of our values, and away we go. So we had 2 scenarios. We wanted to get the service rate to 0.55. And then the second scenario was we wanted to get the service rate down to 0.35. And we've done that. Now, we'll click OK on this. And if we had some waiting cost time per unit and the service cost time per unit, then we can get the total cost. Notice this, again, this is mimicking the total cost equation. Okay? The waiting cost per unit and the service cost per channel, okay, gives us the total cost per time period. By channel, they're talking about the queue. Now, as I'd mentioned, you really do need to look at 511 through 516. And they will take over here. And here's a nice diagram. This is the Burger Dome, but with a 2-server waiting line. Okay. Now, here's where things can get inordinately complex. Okay. I want to talk about that for just a second. This is a customer arrival. We have a waiting line. And then we have 2 servers, server A and server B. And this is a first come, first serve. The customer goes to the next available server. And then we assume the customer leaves after the order is filled. Okay. But it doesn't work like that in a restaurant. It might in a fast food where effectively the customer's out of the queue. But if you're in a restaurant, you get seated at a table. You don't leave after you order your food. You leave after you've gotten your food. And that's when your order's filled. And that's when things can become very dicey. I don't care if you're looking at 1 server or 2 servers. Then that adds some additional time. What is our service time? Now I said you want to take a look at over at page 511 as it walks you through this issue with the Burger Dome. That is the single file we've been working with. And again, we've got these rates of arrival, distribution of service time, and to further reinforce it for you, and I really think to get the best, let me suggest that you do this. Start over here at 11.1, the structure of the waiting line, and go back through that again. Remember, we started with single arbitrary. I think you want to take a look at this again because they talk about Burger Dome in the sense of this as seeing the single server waiting line. And there we are. We have customer arrivals. Then we have a waiting line. Then the server is filling the order and the customer leaves. This is our system. And remember earlier I talked about uncontrollable, semi-controllable, and supposedly highly controllable kinds of processes. The customer arrivals, I have no control over. Oh, I do theoretically through marketing, and I talked about doing some promotions and placement of my retail establishment and all that stuff. But we know if it follows up a song, we're going to have a buildup of people and then it's going to drop. Then we have waiting line, and that's semi-controllable. And the authors here talk about some things. And you've had that experience if you've been at a Disneyland or Six Flags or somewhere like that, or if you've walked into a restaurant that's really busy and they have a place for you to sit. Sometimes, if they're smart, they'll say, if there's anybody here who would like to go to the bar and have a drink or so, when your table's ready, we'll put you there. Okay. Then you've got the server order the filling. A server who is filling the order, and then the customer leaves. Okay. So they're going to walk you through that process and this is the simplest of all of these waiting lines. And we start to look at the arrival rate. The arrival rate is exceptionally important. We've got to understand that and know that in order to determine should we have 1 server, 2 servers, should we have 1 line or 2 lines? as we build the queue. And what kind of queue discipline should we have? When people call and they reserve a table, that's first come, first serve queue discipline. For the simple reason that they order and they're there at a certain time. And a lot of restaurants would say, well, if you're not here by, if you're 20 or if you don't call and say I'm running late, they'll give your table to somebody else. Big cities, top, 5-star restaurants, if you have a reservation at 8 o'clock, unless you are one of the beautiful people or somebody everybody knows or celebrity, you show up 10 minutes late, you're not getting a table. You're out of luck. So a word to the wise. Okay, I think that covers pretty well the Burger Dome problem and what we saw again, and we'll just, I'll put this down here, is that we can reduce waiting time by increasing the service rates. Okay, I'm going to do something kind of different here, and let's do this. I'm going to walk out of the changes that we've made. Go back to our raw, okay, where we were, and we have our arrival rate. Okay, and notice this. Let's look at the equation for a second. The arrival rate equals B7 over B8. Okay, the arrival rate over the service rate. That's the waiting time. Now let's look at these other probabilities here. And it's 1 minus the arrival rate, okay, divided by the service rate. And you can see the trade-offs implied by this. Then we get the average number of customers. This gets a little bit more complex in terms of equation. But you can click in the formula bar and you can see the average number of customers in wait line. Time a customer spends in the waiting line. It's the average time. The average time a person spends is in the whole system. And remember, the system is people waiting, people being served. Okay? And then the probability that somebody has to wait. Okay? And we can play around with the arrival rate. But notice that while the arrival rate is uncontrollable to a great degree, Poisson distributions, we're using probabilities, so we're talking about random effects, or 1 minus random effects. The service rate, we can do something about that. Let's see what happens if we take the service rate and we just improve it by 10%. So the service rate here is 1, and I'm going to change that to 1. I'm going to improve it. So I'm going to change it to point. Well, no, I want to improve it. I'm going to make it 1.1. Okay. Now let's see what happens. Now, you'll notice that by changing the service rate 10%, so we're going to do a little bit of sensitivity analysis here, right here. Service rate. And the service rate is plus 0.10. Okay. And the weight, I'll put the weight probability. Okay. And it becomes and it goes down 0.07. So for every 10% we improve in terms of the rate of service, we reduce the probability of waiting by 7%. And so if we use this as a sensitivity analysis, it's pretty simple in terms of the bang we get for our buck. If we invest some money in training employees or getting new technology, it's not a one-for-one trade-off, but it's not bad. Not bad at all. I'm close to a one-for-one trade-off. So that would be one way to look at it if I wanted to know the sensitivity. So really for every 10%, I get a 7% reduction in the probability that an arriving customer is going to have to wait. That makes sense, okay? When I have this kind of single service operation, this is tempting to say, well, wow, if I put in two service nodes, all right, I can really go to town and I can produce exceptionally fast service. Okay. Now I could put a price tag on this, and let's say that I bought some new equipment, and to get that 10% increase in service rate and the corresponding 7% decrease in the probability the customer will wait, that cost me $25,000. Okay. And this is pretty simple then. I can just say, every percent, and I can take equals by 7, that's the percentage. For each percentage reduction in the probability that someone will wait, I invest $25,000, and for each percentage that I reduce the probability of waiting time, it's cost me $3,500 to do that. Okay, and so I want to make sure if it's worth it to do that. Okay. That's why arrival times become so important. Because if we spend $25,000 to lower the probability that somebody has to wait, then we better make sure that we're dealing with enough people, i.e. enough arrivals, to make it worth our while. Well, some food for thought. As I promised you, this is the supplemental. On Wednesday. We'll look exclusively at the outliers case, and we'll go through it in the spreadsheet and have a good time. So I'm going to stop the share and end the meeting.